Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about hypothesis testing, statistical hypothesis tests. Well, what I want to do to begin this is let's recall our story of crocodiles. So, I don't know if I can spell it. It's crocodile. Jeez, crocodiles. And we said this is for male African crocodiles, like you might find in the Nile River. And we said that the average weight of crocodiles was known to be 14 feet long. 14 feet, and that the standard deviation is 2.5 feet, and we're going to give it one more, and we're going to assume the length of crocodiles is normally distributed. Okay, so let's do something. The first thing we're going to do is we're going to find the probability of randomly selecting one crocodile that's only 12 feet long. One crocodile that's only 12 feet long. Well, in order to do that, I'm going to draw a big normal curve over here. I'm going to smooth it out a little bit. You'll see why in a moment. So, this is my normal distribution for crocodiles. We have a mean of 14. Now, let's go 1, 2, and even 3 standard deviations below, and 1, 2, 3 standard deviations above. Now, we're only concerned in this case about crocodiles that are a length of 12 feet. So, let's see. If I go 1 standard deviation below the mean, that would be a crocodile 11.5 feet. And I could continue this. I could go down to 9 feet, and we could go down, make them even smaller if we wanted to, but that's going to be unnecessary. Also, we could make these crocodiles larger. We could go up to 16.5 feet. That would be 1 standard deviation above the mean. And we could even go again to a crocodile that's 19 feet long. That would be 2 standard deviations above the mean. Now, here's what we want to do. Let's find the probability of a crocodile that's less than 12 feet. So let's do that in white. Or we'll continue with this green, because we're going to need a few colors here today. So what that is I can't make this. Well, I guess I could. 1, 2, 3, 4. So right there, that is 12. And we want this area right here. This represents the probability of a crocodile that's only 12 feet long. And remember what we need to do is we need to calculate the z-score for 12, and that gives us a 12 minus 14, and then we divide that by 2.5. And I need my calculator here. This is going to be minus 2 divided by 2.5 is the same as 5 halves. So that's the same as negative 2 times 2 fifths. So this is going to be a negative 0.8. Negative 0.8. And if I look this up on my table of z-scores, I'm going to do that here. Let's see, if we do that, what we're going to find is, oops. So if I look up at negative 0.8 on my table, what I find is the probability of finding that yellow region is 0.2118. Now, let's just say you're a more determined researcher and you're willing to sample a group of 4 crocodiles. So let's do that first. So we're going to have a group of 4. So n is 4. So we want the probability now of finding an average of crocodiles that are less than 12 feet. Now think about what happens here for a moment. What happens, there's a key piece in this, and that is that the standard error of the mean becomes the 2.5 divided by the square root of the sample size. Well, that's 2.5. I'm going to write it as 5 halves. It's a little easier for me to work with the numbers in my head. Divided by 2. That is the same as 5 fourths. Well, wait a minute. Our standard deviation now went from being 2.5 to 5 fourths, just a little over 1 1/4. So I'm going to use let's use this pretty blue for a moment. So in other words, these tick marks here that I have in yellow are in halves. So 1, 2, and then right there, that would be 1 standard deviation from the mean now. So in other words, in 2 standard deviations, it would be halves. Oh, goodness. 5 fourths. So 2 standard deviations is going to be 10 fourths. Sorry, that shouldn't be so hard to do. 10 fourths, which is 2.5. So look at that. That puts me exactly right here. 11.5 now is 2 standard deviations. Well, what has happened? What has happened is this. The central limit theorem is going to tell me now that my curve has gotten pushed way up. Way up. So now the probability of finding a group of 4 crocodiles that are less than 12 feet, well, it's just this little blue region, and of course that would go out towards infinity. So it's just this little blue region, and so I think my calculations should give me something smaller. Well, let's see if that's correct. So now I take 12, subtract the 14, and I divide it by the 5 fourths. Well, this is going to become a -2 times 4 fifths. Yeah. But that's going to be -8 fifths. I think that's -1.6. Well, if I look at that up on my table, what this comes out to be, oh, this shouldn't be I made an error. I shouldn't have written the probability equals that, because it doesn't. That's just the z-score right there. So we're just going to move that down. There's my z-score calculation. So, but the probability is 0.0548. Wow. So hold on a minute. The probability of randomly selecting a group of 4 crocodiles is only 5%. Well, let's just say you were an ambitious researcher and you went one more step. You went all the way to orange, and orange is when you have groups of, say, 16 crocodiles. Well, at 16, what's going to happen to the standard error of the mean? Well, that's going to become a 2.5, which is the 5 halves, divided by the square root of 16. That's 4. This is going to be 5 eighths. 5 eighths. So when I calculate the z-score now for 12, that's going to be a 12 minus the 14 divided by 5 eighths. Well, that's going to give me, let's see, a -2 divided by 5 eighths. Well, that's going to be -16 fifths. Holy smokes, -16 fifths. That's going to be 3 1/5. That's a fifth is 0.2. That's -3.2. Well, wait a minute. What just happened now? Our standard deviation now got so small that 3 standard deviations is 2 standard deviations is just over 1 unit. So it's 10 eighths. And 3 standard deviations is 15 eighths. So it's not quite 2 units. In other words, 3 standard deviations is only right there where the 12 is. So now, in other words, 3 standard deviations, the curve is essentially on the axis. Now my whole curve got pushed way up there. It should be straighter than that, but mine's not. Yours probably will be. So now this probability is just this little orange sliver. It should be tiny. Let's check our calculations. So our this is the probability that x bar now is less than 12. Well, this is, if I look up negative 3.2, the answer is 0.000. I almost put 7 there, but no, there's another 0 and then a 7. And here's the question. When would that occur? Isn't that just seem strange? It's easy to pick a single crocodile that's less than 12 feet, but to pick a group of 16 crocodiles that are less than 12 feet, well, that's pretty improbable that that would happen. If you were the researcher and this happened, right then, once you've experienced the improbable, you have reason to look into that. That should not happen. So that's what I want to look at now, is when you have discovered, so when the improbable becomes probable, a test of hypothesis is in order. Now, what do I mean by that? That's kind of a general statement, and that's okay. What I mean by that is that you shouldn't be able to see these things. And so if you did this, if you might have been the researcher and you thought, wow, the crocodiles in this pond are just smaller. What might have caused that? Well, it could have been things like maybe it was a small pond. Maybe you just have a small pond. You know, in the same way that goldfish don't get very big when they're kept in a jar, but if you put them in a lake, they can get quite large. Or a bonsai tree stays small because it's in a small pot and its roots are bound. So maybe you have a small pond, and that's restricting the growth of the crocodiles too. Or it's just a small body of water. Maybe there's some kind of environmental influence. Environmental influence. Maybe there's toxins in their water that just aren't allowing them to grow as large. Or 3, maybe there's some predator. Maybe there's some predator that just keeps eating the crocodiles. Well, the predator might also be man hunting the large crocodiles too. But for some reason, this shouldn't happen. You should see crocodiles that are larger than this in this pond. And when you encounter something like this, then what you want to do is you want to test your intuition. And here's how the test works. The first thing you want to do, is you want to state a null and alternative hypotheses. Hypotheses and identify your claim. Well, here's how you write that. Here's how you write step 1. I'm going to use this yellow. I think it's a little easier, or the white's easier to see. You write our null hypothesis, and let's make some good notes. Null hypothesis. Your null hypothesis, it's written as H sub 0, and you write its mu is equal to, well, the known population length of crocodiles is 14. Okay? Now your alternative hypothesis, it's written as H subscript 1, is what you believe is the is what else is happening. In this case, you believe that the length of crocodiles, at least in this body of water, is less than 14 feet. That's your claim. That's what you're going to try to prove. Now, before I go on, let's make a few notes. The first one is the null hypothesis states that two parameters have no difference. Have no difference. Or you could say two parameters are the same. Or, I'm sorry, equal parameters are equal. Well, what would that mean? That would mean that we would expect the mean in our body of water when we look at our crocodiles to be the same as the mean for crocodiles all over the Nile River. Now, the alternative hypothesis, I'm going to abbreviate hypothesis, HYP. The alternative hypothesis states that parameters are different. Okay, this is a big deal because if our researcher was to show that for some reason the crocodiles in this body of water are significantly less than 14 feet, then people should know about that. They need to find out what's happening. But that's just it. That's the next piece. How would I decide if what we're observing is significant? So that's our next piece. So our next piece is we have what's called a level of significance. A level of significance, and we denote it as alpha. Alpha equals the common levels of significance are 0.10, 0.05, and 0.01. Now, what does this mean? The level of significance means that if you find that the probability of your results is even less than alpha, meaning what you found is completely unbelievable, then, or is to the point of either 0.1, 0.05, or 0.01, then you have made a very, very convincing argument that something is different in this case. In other words, what you would say is you would reject the null hypothesis. And before we do that, though, let's just decide. So before you do your test, you have to identify your level of significance. I know researchers identify alpha before the test. Okay. So what does that mean? What that means is, in our case, we're interested in crocodiles that are less than 12 feet. So if our researcher is to go out and measure a number of crocodiles and find that they're larger than 12 feet, the average of those is larger than 12 feet, well, then obviously that's not significant to what we're stating, and that's that crocodiles are shorter than 12 feet. So what we would do is we are only concerned about short crocodiles. Well, short crocodiles are found out here in this tail. And for the sake of this problem, let's choose alpha as 0.10. So alpha equals 0.10. So that is this region. And we call this the critical region. Critical region. Because if our probability is that, it's a critical finding. Now this unshaded area, we call this a non-critical region. It's a non-critical region. And the key here is what separates the critical region and the non-critical region. We call this a critical value. So we need to find our critical value, and in this case we're using 0.10. So what do? Well, what we do is we look up on our table 0.1. Now when you do this, you look this up on your tables and you'll see like 0.0. Oops, let me get closer to where I should be. Oh, I see values here. Here's like 0.102, 0.1003. Well, if you found 0.1003, your argument would be that it was almost, but not quite significant. So to be conservative, I'm going to use 0.0985, a little less than the 0.1. So what that did is I looked on my tables to where I found a 0.1. What did I find? 0.003 and a 0.0985. So I decided that the 0.985 is more conservative than being a little more than the 10%. So then I looked back over here and I found my z-scores, my associated z-scores. And on the left, I have a negative 1.2, and on the top, I have 0.09. So my critical value, which is often just abbreviated CV, in this case is negative 1.29. Okay? Negative 1.29. So what we've seen now are the first two steps in a test of hypothesis. The first one was to state our null and alternative hypotheses, which we did. Our second one is to identify the critical regions, non-critical regions, and find a critical value. Now our third thing to do is to conduct the test. So let's do that. So our third step, number 3, is conduct a statistical test. Okay, well, so there's a little caveat here, and we just need to identify when sigma is known. Okay, and ours is when sigma is known, the test is just a z-score. The test is z equals x bar minus mu divided by the standard error of the mean, which is just sigma sub x bar, or and I'm going to put it right this way, where sigma x bar is sigma divided by the square root of the sample size, n. Okay, so let's just suppose our researcher, and it might have been a team of researchers. I imagine wrestling crocodiles, it may take more than one person to do this, but suppose our researchers sample 16 crocodiles. 16 crocodiles, and find the sample mean. Find the sample mean is x, I don't even need, is 12. Well, we've already done this calculation, but let's try it again. What that would mean is that sample mean, this piece right here, that is x bar. So I would say that my test says z equals x bar, that's 12, minus the mean. Now this is always the known population mean, mu, the same mu that we used in our statement of hypotheses. So 12 minus 14 divided by, and then we said that the standard deviation is 2.5. We're going to divide that by the square root of the sample size, which is 16. And this gave us, if I remember correctly, a negative 3.2. Negative 3.2. Now, here's what we do with this. The negative 3.2, this is the key part. This negative 3.2 is a z-value, but it's a test value. So what we do is, remember, these are z-scores that are on the horizontal axis, and in this picture, they're really going to be test scores. Well, my test score is negative 3.2. Well, if I put that on my picture, that is somewhere out here. It's in the critical region. What that means is that what our research team has witnessed is, in fact, statistically significant. That's what that means. So let's go over here. Let's write that down. So this is actually what's called the decision. So this is step 4. Is called the decision. And the decision says that since z, we'll put the test score, the test value, is in the critical region, this is really, now this first sentence here, this first clause is just for clarification, but the bottom line and what you'll see people say is since it's in the critical region, reject the null hypothesis. Reject the null hypothesis. And what that means is that when you're looking at this body of water, something about the length of crocodiles is just, it's not 14 feet. Okay, now we could have had the other thing that happened. The other situation would be this. So this is what our data gave us. But what if the z-score didn't lie in the critical region? Well, if that was the case, we'd say when z is in the non-critical region then our decision is do not reject the null hypothesis. It's that simple. Do not reject the null hypothesis. Okay, so those are the two different things that can happen regarding our decision. And it's always about the null hypothesis. We either reject it or we do not reject it. Now, what it doesn't mean is it doesn't mean that we prove the null hypothesis or the alternative hypothesis, and nor does it mean that we now accept the alternative hypothesis. All it means is that in this case, the evidence supports the claim. And that's our final conclusion 5. And then I want to come back to this. The conclusion. The conclusion connects the decision to the claim. Remember, that's what our investigators, our researchers saw. They'd seen some crocodiles and thought, boy, these crocodiles here sure don't seem like they're 14 feet. Let's test that. And that's our claim. So in this case, what we would say is the evidence supports, that's PPOR, supports the claim that the length of crocodiles in this area is less than 14 feet. Now, I wanted to share one last piece. Those are the 5 steps. That's how you conduct a test of hypothesis. Now, you can have a few different conclusions. But what's really important here is why we say it doesn't prove the null hypothesis. And here's an interesting little case study, and it was called the black swan. So at the time, the people writing the taxonomy books about the animals and their genus and their species were mostly coming out of Western Europe. So in Western Europe, all the swans were white. So all of the researchers had only seen white swans. So they said, therefore, swans are white. So their null hypothesis was that swans are white. And they wrote the books as a white bird being one of the key factors for a swan. Well, then what happened then is in 1697, a Dutch explorer and his team of researchers went to Australia. And in Australia, they found a bird that, darn it, it looked just like a swan. But guess what? The only difference that they could see was it was black. And so all those years, all of our evidence, all of our observations had supported our null hypothesis. But then when we got new information, all of a sudden we found out that, wait, now we can reject. So in 1697, we rejected the null hypothesis that swans are white. In fact, we found out swans can also be black. So what is that? So does that mean that the average length of crocodiles has gone down to 12 feet? We don't know. All we can say is that the evidence that we have on hand today supports that the length of crocodiles is less than 12 feet. Just like back in this before 1697, they could say, based on all the evidence that we have had, all swans are white. This is called inferential logic or inferential statistics. And what that is we generalize to the population based on observations. So we make observations, or in our case, we're statisticians, so we don't call them just observations, we call them data. We use our data. And from our data would say everything that our data supports is that crocodiles are shorter than 14 feet. And so we make a generalization to the whole. Is it flawed? Of course. However, it does work quite well. Welcome to hypothesis testing. I hope that helps, and thanks for watching.